Hello, my name is Mohit Prabhashankar, and this is our presentation about contrastive explanations in neural networks. I thank the program and session chairs and all the organizers for having this conference in a virtual manner during these times. In this paper, we question the status quo of current explanatory logic in neural networks and show that a more intuitive explanatory module can and should be explored. Let us start by discussing about explanations. Explanations are a set of rationale or arguments that are used to understand the reasons behind a decision. Consider the image of the bird on the left. Ask the question about what the name of the bird is. The correct answer is it is a spoonbill. A simple follow up question is why spoonbill? The answer to this question involves a rationale or explanation supporting your answer. Your explanation can take the form of something like shallow water birds with a flattened beak and football shaped body and so on. This is a language based explanations. We use words to describe a spoonbill to explain our answer. A similar explanatory module is a visual explanation. Instead of language and arguments and rationale, visual characteristics are used to justify a decision. This is shown as an image on the right. Note the areas highlighted in red. These are important reasons in your decisions. The blue area is not so important. Yellow and green is somewhere in the middle. Consider the similarity between our language-based Y spoonbill and visual-based Y spoonbill. The highlighted regions are in fact the same features highlighted by the arguments. The flattened beak, the pink and football-shaped body are all part of the explanation. We can see that these explanations, either language-based or vision-based, both try to answer the why questions. In other words, they try to provide causal factors that explain the decisions. Whether they succeed in these causal representation is another issue and not something we will tackle in this video. In fact, the explanation about the spoonbill that we have seen till now is Grad-CAM, a popular visualization technique. Other techniques exist which try to explain the presence of the spoonbill in the image. These include guided backpropagation, positive saliency, smooth gradients, vanilla backpropagation, among others. Clearly, all these techniques are answering why P questions, where P is a spoonbill. All techniques and methods assume that the explanatory nature is causal, that is, answers to why P questions. In this paper, we question this nature of explanations. We posit that intuitively, explanations are not always causal, rather, they are contrastive. Let me provide a motivation based on writing papers. When we write papers, we highlight our paper's novelty, its contributions, and its impact to the field. I want us all to remember how we do this. We don't build up our novelty from the ground up. Rather, we assume that the readers have some knowledge about the field in general. We explain existing works from a very high level and then contrast our work to theirs. We show what is missing in the related works, and the rest of the paper is about how we fill this missing piece of information. In other words, we explain the need for our paper's existence contrastively. Now let's take this concept of contrastive explanations to visual contrastive explanations. Going back to the spoonbill example, the why spoonbill question is answered through Grad-CAM. For the contrastive explanation, we need a contrast to compare against, similar to related works. In this case, let us assume that the contrast is a flamingo. Personally, I chose this example because I knew of flamingos before, but not about spoonbills. So for me, if I were asked to visualize spoonbills in my mind with a description that said that a spoonbill has a flattened beak, a football shaped pink body, it did not conjure up the image of a spoonbill in my mind. But when I was told that spoonbills are similar to flamingos, except that their legs are shorter and their necks are not S shaped, I was able to visualize. That, in essence, is a contrastive explanation, an answer to why spoonbill rather than flamingo, and more generally, why P rather than Q questions. The visual counterpart of this explanation is a contrastive visual explanation. For the rest of this video, we will be calling them as contrastive explanations for brevity. The objective of the paper is to derive these contrastive explanations from pre-trained networks. Note that Grad-CAM and other explanations to YP questions are also extracted after a network is trained. We also want to be able to do this on a wide variety of data and applications. However, there are no contrastive ground truths that the network has trained on. Rather, it has trained on a supervised set of labels for some data. The objective for us is to then define contrast from a visual and representational perspective, and then extract such a contrast in an unsupervised way. This leads us to the overall structure and novelty of our paper. We first formalize existing structures of explanations before defining contrast and extracting them. We then apply them in two applications: recognition and image quality assessment. Doing so provides our novelty. We question the nature of current explanations and formalize them through first order logic. And then the method itself is a simple and intuitive extension to existing techniques of YP explanations. As we saw before, all existing techniques answer the question YP. Particularly, let's take the example of spoonbill. These explanations answer the first part of our ultimate question, that is, why P within the larger question, why P rather than Q. Hence, if P is the prediction spoonbill, Q is the contrast. We define the contrast Q in the visual space as the perceived difference between two known quantities. Note that known is important here. A network has to be trained to know a spoonbill and a flamingo. In other words, contrastive explanations are derived from trained networks. In this case, we were using VGG16 trained on ImageNet dataset. Consider the spoonbill image given to a trained architecture. Let us assume that the network classifies the image correctly as a spoonbill. Within the network, the image falls on a trained manifold. Since the prediction is correct, consider that the shown plane is a simplified learned manifold where a spoonbill is classified as a spoonbill. Note that the weights span this manifold. Hence, projecting onto this manifold provides the correct decision. Now we define contrast in the representation space. We define contrast to be the distance between two manifolds, one in which a spoonbill is classified as a spoonbill, and another in which a spoonbill is classified as a flamingo. In other words, it is the distance between two manifolds, P and Q, where an input image X is classified as P versus the same image X is classified as Q. The next question is how to characterize this distance. Now we come to the technical core of our method. We already know that the weights span the manifold. The gradients with respect to the weights show the direction of motion of the weights when going from manifold P to manifold Q. Assuming that the image of the spoonbill falls on the manifold P, where it is correctly predicted as a spoonbill, the gradients of loss function between classes P and Q shows the movement between the two manifolds. This is illustrated in the diagram to the right. Hence, contrast between P and Q is the gradient dj by dw from any particular layer. Note that Grad-CAM already provides a YP framework. It backpropagates the score of the class that the network predicts to determine the explanation to YP questions. The gradients, when backpropagating the logic, provides an important score within the framework. Instead of using the score gradients, we use contrastive gradients in the same framework to obtain our explanations. In fact, the only change in code is shown below. On the left-hand side, we have Grad-CAM. On the right-hand side, we have our contrastive explanation. Note that in Grad-CAM, the term score is calculated by passing the image through the model and taking only the required score from the logits. In our framework, a cross-entropy loss between the logits and a one-hot vector with one being in the position of the required Q is backpropagated. Everything else in the framework remains the same. We now show some results in two applications. Let's start with recognition. The first column shows the input image to a trained network. The second column is its Grad-CAM answer to YP, with P being the labels. The third column consists of the first considered contrast, Q. The fourth columns are their contrastive explanations. The fifth column is another contrast for the same P from column 1. The sixth column is its contrastive explanation. Notice the different results. We already saw the contrast between a spoonbill and flamingo. Notice the contrast between a spoonbill and a pig. The neck, beak, and legs differ between the two. Consider the Bugatti convertible and the coupe. The contrast lies in the open top of the convertible. These are all human interpretable. That is, we can relate to the results. The grayed out results in this case are human interpretable. The results in purple are the same as Grad-CAM. This would mean that the same features used to say YP are also used to find YP rather than Q. Consider the question in the second row. Why bulldog rather than a blue jay? To show that the image is a bulldog, Grad-CAM highlights the face of the dog. To show that the image is a bulldog rather than a bird, contrast also highlights the face of the dog. That seems intuitive enough. If there is no fine grained difference between the bird and dog, then the same features used to make YP decisions can also be used to say YP rather than Q. The next interesting result is the non human interpretable result. Consider the contrast between the stop sign and no left sign. Given these images, humans would say the explanation to why no left rather than stop sign is that there is a lack of the letters S, T, O, P. However, the network thinks that it cannot be a stop sign based on the bottom left highlighted portions. This is because, as we mentioned earlier, the network has learned only to differentiate between objects in a supervised fashion without any contrastive information. In this case, there are 14 signs taken from CureTSR dataset, all of which are shown. Notice that stop sign is the only sign with a straight edge in the bottom left. Seeing that there is no bottom left edge in the no left sign is enough for the network to make the decision that it is not a stop sign. Hence, contrastive explanations provide an added layer of understanding to networks that are not easily interpretable. In fact, we explore the benefits of contrastive explanations further in the next application, image quality assessment or IQA. IQA is the objective assessment of the subjective quality of an image. Consider the distorted image shown above. Putting it through an IQA algorithm, the quality score of the image turns out to be 0.58. In this work, we use DIQAM IQA metric. The reasons being that one, the authors provide a pre-trained PyTorch code that we were able to implement, and two, the network is end-to-end. That is, we can backpropagate loss directly with the predicted score P as 0.58 and and contrast it against any score Q between 0 and 1, with 1 being the best quality and 0 being the worst. We first run Grad-CAM on the input lighthouse image as visualized in the heat map overlaid image on the right. As can be seen, all parts of the image are being used to make the decision that the quality is 0.58. However, no other fine-grained information can be derived from these Grad-CAM images. Now, we use contrastive explanations. A loss between the predicted score 0.58 and contrast 1 is backpropagated and visualized similar to Grad-CAM. As can be seen, all the foreground portions of the image, house, lighthouse, and cliff, are highlighted. This means that the distortions in these foreground objects prevents the network from predicting a high score. Now, if we reduce the contrast to 0.575 instead of 1, notice that the highlighted portions are from the house and lighthouse only. Hence, this suggests that while all portions of foreground played a part in not predicting 1, the house and its corresponding distortions are more important since their presence is preventing the network from predicting 0.75 as well. It would have given a pass and predicted the quality as 0.75. The distortions were localized to the cliff only. But since the distortions exist in the house, the network decides to give a lower score of 0.58. Now let's consider the other side. Why did the network predict the score as 0.58 rather than a lower score of 0.5? Interestingly, the network for the first time highlights the sky. The good quality of sky and lighthouse leads it to believe that the quality is higher than just zero point 0.5. When we lower the contrast to 0.25, most of the sky, along with the lighthouse and cliffs, are highlighted. This indicates that the score is higher than 0.25 because of the great quality of these parts of the image. The same set of experiments was conducted on a different image, and the results are shown. A number of conclusions and observations can be made about the way the network analyzes quality based on these images, not least of which is that the distortions in foreground lead to a lower quality and the background increases the overall quality, assuming the same type and amount of distortions exist. Just this conclusion is something known already to researchers in the field. However, seeing it visually in action can be both enlightening and heartening that the network has learned the principles of IQA without explicitly coding the principles of IQA. This brings us to the summary and end of this video. We conclude by reiterating our contributions. We provide structure to existing Grad-CAM like explanations. We question the nature of these explanations and showed that contrastive explanations exist and are intuitive. That these contrastive explanations can be extracted from pre-trained existing networks in an unsupervised way. Unsupervised because we did not use any image of flamingo or IQA quality image of 1 to obtain contrastive explanations. Please check out our PyTorch codes in our lab GitHub repository and our other related works to this field in applications like anomaly detection, saliency, and robust recognition from our lab website. Thank you.